So this is the formal notes section of our course. By now, you've already interacted with both of the group work activities. So let's get started. I'm going to use a different color than black. So a graph is a collection of edges and vertices. So in math language, that is G equals the set of the edges and the vertices. We usually refer to the set of edges as E and the set of vertices as V. The V of G also is known as the vertex set. And E of G, or E, is the edge set. We have vocabulary words that denote or refer to the number of vertices and the number of edges. The order of a graph is the number of vertices in G, and the size of a graph is equal to the number of edges in G. So in this example below, what do you think the edge set is? What do you think the vertex set is? I'm going to give you a minute to try and figure it out. So the vertex set is A, B, C, D, and E because it refers to all the dots. Okay, those are the vertices. I'm going to erase these now. I'm going to erase these circles because they'll be distracting for what I'm about to do next. The vertex set, or I'm sorry, the edge set. The edge set is AB. Now, when we mark edges, we mark when we name edges, we name them by the vertices that contain them. AB is equal to BA. I don't care which way you do it, okay? Just got to do it this way. So the edge set, AB, AC, AE. Now, these squiggly lines are important because they indicate set notation. So when we're writing out a set, we have to go with the name equals and then the squiggles. To continue with this, we've got AB, AC, AE. Now we're going to go BE, BD, BC. Now we're done with the B's. So now we're going to go CD, DD. This kind of edge has a special name. It is called a loop. So to continue, we have one more edge, and that is DE. The order of this graph G, so graphs are named, this should be over here. Graphs are usually named with a capital letter. We use G a lot because G graph, but I'm going to throw different letters at you sometimes. So just be aware of that. So the order of G is 5. And the size of G is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now, next page. When we have more than one edge connecting two vertices, we call the edges multiple edges. You might see the word double edges, but I don't like using double edges because that implies there could only be two. But if I have two vertices, A and B, I can connect these multiple times because the edges are the relationship and the vertices are the things that are being related, and things can be related multiple times. And then, the rest of the graph will be out here. So I'm going to draw another picture. I'm going to have this vertex be U and this vertex be V. And I'm going to connect an edge between them. And I'm going to call that little e. Because I'm about to throw some math language at you. So for U, E, V, we say E is incident to vertices U and V. And then we say vertices U and V are adjacent. These words pretty much mean the same thing, okay? They just both mean connected. An isolated vertex has no edges incident to it. So an isolated vertex has no edges connected to it. So here's an example. This is a disconnected graph of isolated vertices. My vertex set is A, B, C, D, and E. My edge set is the null set. It's also known as the empty set, so it's a set with nothing in it. So since graph theory is the study of relationships, we can use it to describe actual relationships. So a few years ago, and I'm thinking a few years ago, like 2010-ish, there was this app called the Facebook Friend Wheel. I found these on a Google search because they go on the internet. So what these graphs represent is the Facebook profiles. Okay, these are profiles. Now the edges represent a relationship between the profiles. So if we zoom in, I mean, you're not going to be able to see these names, but we can at least look at this graph. So if I had this profile, say this is Jim, and this is Claire, they are vertices in our graph. The fact that they share a friendship, or their profiles are connected, allows us to draw an edge between these 2 points. If we look at a much bigger graph of a much more connected person, such as Rachel Ray, we can see that that graph gets intense really quickly. And this also is, these graphs are also showing mutual friends. So who's friends with who? And I think it's a fascinating thing to think about this in terms of Facebook, because those graphs can essentially be infinitely large, because Facebook gets millions of profiles every day, and then everyone is connecting. And I think it's really interesting, and I would love to see and be able to compute some of the beautiful things that we can do in graph theory on a Facebook graph. But that is far beyond the scope of this class. So let's fill in these lines in our notebook. So the vertices here represent profiles, and the edges represent friendship. So here's another graph that we can look at. This is also a place where this stuff is applied. Sociologists use larger scale relationship graphs to study specific relationships. This was taken from a study, Chains of Affection, the Structure of Adolescent Romantic and Sexual Networks, from the American Journal of Sociology. And you can see that each and every person, each and every vertex represents a person. And every edge represents a relationship. Now, if we look here, we can see there's a whole lot of relationship going on. This was in, if you go and read the study, this was conducted in a high school. So this picture can tell you exactly what was going on in that high school, and I'm jealous because that was not going on in my high school. So now let's look at what happens when we are only given a vertex and an edge set with no picture. We can draw these graphs in multiple different ways. So we have a vertex set here. We have A, B, C, D. So I'm going to draw that. A, B, C, D. And I'm going to label my graph. A, B, C, D. Now my edge set is saying I'm connecting A to B. I'm connecting A to C, A to D, B to C, B to D, and C to D. I can draw this differently. And you may or may not have a picture that looks like this. These graphs are called isomorphic graphs. Because they're the same graph essentially. So all I did is I picked up this C and I moved it in here. So let's move on to some graphs and terms, because we need to establish a mathematical vocabulary for when we're finding these patterns and trying to figure things out. So we're going to talk about the degree of a vertex. Okay? The degree of a vertex is the number of edges that are adjacent to it. So when we talk notation, we say degree of the vertex, say A, and in this graph the degree of A is 3 because there's 1, 2, 3 vertices coming out of A. Obviously, that number is going to vary depending on how many vertices you have, how many relationships you have. So if I draw this example, and I'm going to even give us some multiple edges and some loops to work with. Okay, so here the degree of A is 1. The degree of B is what? 3. The degree of C is 5. And let me tell you why. Because I know that some of you just said a different number. When we have a loop, we have 2 ends to that loop. There's 1 end, there's 2 ends. Okay? So here, the degree of C is 5. The degree of D is 3. The degree of E is 2. The degree of G, 1, 2, 3, 4, 5. And the degree of F is 3. Fun fact about graphs, a graph will always have an even number of odd degree vertices. Now, I know that I will eventually stop saying degree, and I'll just refer to a vertex as even or odd. So if we look up here, this is an odd degree vertex because it has 1 degree. So it is 1. It is an odd number. This is an odd. This is an odd. This is an odd. This is an even. We have 1, 2, 3, 4 odds, 1 even. Okay? It is absolutely possible to have an odd number of even vertices, but it is not possible to have an odd number of odd vertices. The whys to this are in a homework question, so I want you to think deeply about why this could be always true. Okay? So now we're going to talk about cycles or walks. I don't actually like these definitions, and I really need to take them out of the book. So let's discuss what a path is. A path is open. So that means it starts and stops in different places. There are 2 types of special paths that you're going to learn about. You're going to learn about an Euler path and a Hamilton path. But you're also going to learn about non-special paths. So if I drew a quick picture here, and we're going to use this for both definitions. We have a graph that looks like this. This is my go-to. This is a complete graph with 4 vertices. You'll also learn what complete graphs are later on. If I wanted to make a path, oh no, what are you doing? Stop. Stop that. Stop what you're doing. Say I wanted to go a path from A to D. So I go from A to D. I could go that way. It would just be A, D. Or I could take another way. Let me grab another color. I'm going to go A, B, C, D. Paths can be of any length. So the length of a path or cycle is the number of edges in that path or cycle. Now let's talk about cycles. You're also going to learn the same special cycles, the Hamilton and Euler cycles. But I'm going to redraw our graph example here. A, B, C, D. A, B, C, D. Now I said cycles are closed. Okay? Cycles are closed. So that means they start and stop in different places, same places. Okay? So A, C, B is a cycle. A, B, A, C, D, B. A, C, D, B, A. I forgot to add the closed vertex. So edges are never repeated. It's in a path or cycle, it is okay to repeat vertices, but not, oh, let's not do pink. Let's go back to our blue. Edges. Okay? Except in a certain case, covered in chapter 2. So they're one of those special cycles and paths deal with not repeating vertices or hitting things exactly once. So there are exceptions to this rule. But as of right now, you're not repeating any edges, but you can repeat vertices. Okay, for this example, we're going to look for a cycle of length 1. Now remember, length 1 means one edge. There's only one kind of cycle that has one edge, and that is a loop. So we will denote that by EE. A cycle of length 2 is 2 edges. Do you see one? It's B, C, B. You could also write it as C, B, C. Either way works. Doesn't matter. Cycle of length 3 is a triangle. There are multiple in this graph. One of them is a DC. Try and find more. So now we want to find a cycle of length 4. Give me the page. Stop being persnickety. So a cycle of length 4, it will look somewhat like a square or a rectangle. It won't be exactly that always. Sometimes it will be. There's one. So that was B, E, D, C, B. Cycle of length 5. So I'm going to let you guys, stop it. Let you guys fill in this table to think about this some more in depth. So those questions. So we're going to talk about connected versus disconnected. A graph is connected if you can get from any vertex to every other vertex in the graph along a path. We can also say the graph is in one piece. A disconnected graph is made up of components. An isolated vertex is its own component. Components are considered graphs themselves, and therefore each component must have an even number of odd vertices. I want you to remember this. These are things that you're going to need. Nope. These are things that you're going to need for homework. Okay? This is a little bit of humor. In a social graph, you are an isolated vertex. Discrete bullying. Not that we advocate bullying around here. So if we look at this example, this graph G has 3 components. An edge whose removal would disconnect a connected graph or a connected component is called a bridge. Here, edge CD is a bridge. And here's your problem set. There are a lot of questions. I believe there are 27 of them. Hey, stop it. I'm sure you will have lots of questions, and I will be around for a homework review online. Check the calendar for when this is due and when I'll be around. Because we definitely will need to go over go over these questions. When you are done, move on to section 2 with the group work for types of graphs.